Hi, my name is Zhu Jiantang, a PhD student in WPI, come from Energy Metal Research Group. Today, I would like to introduce advance in magnesium primary production by reactive cathode molten salt electrolysis with GMAT distillation. Our group focuses on developing a low-cost, low-energy consumption, and low carbon dioxide emission of METS to produce magnesium metal. So what we're gonna do, we want to use molten salt electrolysis, followed by GMAT distillation to produce pure magnesium metal. In molten salt electrolysis part, we want to use SOM membrane and then liquid silver inside the membrane. So we use this way to develop a inert anode. During electrolysis, only oxygen ions will go through the membrane and then lose electrons at liquid silver. So only oxygen gas come out from the anode. So in this way, we produce carbon-free metal. I would like to introduce GMAT distillation chamber to you. In my opinion, this is beauty of my project. As you can see the left picture, magnesium evaporation come out from the high temperature zone and then condense at the low temperature zone. But the energy just lost because the magnesium from gas phase to the solid phase. So the energy just lost. This is the traditional distillation chamber. But in our GMAT distillation chamber, as you can see right picture, magnesium alloying will go through green light, just like this. And then magnesium vapor will go through like blue light shows. For example, in evaporator 2, magnesium evaporation come out from evaporator 2 and then will condense at condenser 2 and heat was released because magnesium vapor from gas to liquid and then heat just release. But the released heat will be absorbed by evaporator 3. So that means the energy just like be reused. So we increase the energy efficiency in GMAT distillation, not like traditional distillation chamber, the heat just lost. For comparison, we conducted 2 experiments. One is SOM as anode, and 2 is carbon anode. As you can see the right picture, carbon anode shows higher current efficiency. But in the energy analysis, as we can see here, the SOM anode means increase the electricity requirement. Okay, but if we use the SOM anode, the carbon dioxide will be eliminated. This is a good. This is good, but use the carbon anode, carbon dioxide will be produced. It's not good because we want to produce carbon-free metal. We also conduct experiment at the GMAT distillation. We put magnesium alloying in Molten chamber and heat the temperatures into high temperatures, expected temperature. So the magnesium vapor just come out from the Molten chamber and then condense at the top chamber. And after compare experiment, you can see right picture. We get pure magnesium, the impurity lower than the 1%. Yes, we still have some problem needed to be figured out. As you can see the right picture, left picture, we can because the thick SOM anode need more electricity requirement. So we want to reduce the electricity requirement. That means you can reduce the energy consumption. So we try to develop a thin SOM membrane. So that in that way we will reduce the electricity requirement. And the schematic diagrams, just like this picture shows. And in the GMAT distillation experiment, we also find the tin maybe will align with the chamber, distillation chamber. I mean the chamber made of sustainable steel. Sustainable steel is okay. So we try to find a coating material to protect the distillation chamber. You know, if we want to do a long-term experiment, I think the corrosion will be a problem. And if we can find a coating material, that will be increase the stability of the chamber. And then we will analyze the process with continuous magnesium oxide feed, and we'll scale up process from bench top to the pilot level. Yeah, we still have some work to be figured out to be done. I hope we can have the good news come from, near future. Thank you very much.